In August 1989, a spacecraft built in the 1970s passed within 25,000 miles of one of the strangest worlds in the solar system. The encounter lasted only a few hours. Voyager 2 had been traveling for 12 years. It had already photographed Jupiter, Saturn, and Uranus. Its cameras were agging, its instruments were tired, and its power was steadily fading. But what it captured during that brief flyby of Triton, Neptune's largest moon, would haunt planetary scientists for the next 3.5 decades. Triton should be dead. It should be a frozen ball of ice and rock, geologically inert, atmospherically barren, its surface ancient and untouched. At a distance of 2.7 billion miles from the Sun, Triton receives less than 1,000th of the sunlight that reaches Earth. Its surface temperature was measured at -391 degrees Fahrenheit, one of the coldest natural surfaces ever recorded anywhere in the solar system. At those temperatures, nitrogen freezes solid, methane freezes solid, water ice becomes harder than steel. Nothing should be moving on Triton. Nothing should be erupting. Nothing should be active in any geological sense. And yet Voyager 2 saw plumes rising from the surface. Dark streaks stretched across vast plains, all of them pointing the same direction. The terrain looked young, far younger than it had any right to be. Craters were sparse where they should have been abundant. A thin atmosphere hugged the moon's surface, an atmosphere that should not exist at all. And in the data sent back across nearly 3 billion miles of empty space, scientists began to notice patterns that made no sense. Patterns they are still trying to explain in 2026. Tonight, we are going to explore what Voyager 2 found around Triton, the discoveries that broke planetary science, the anomalies that defied every model, and the questions that still have no answers. Because Triton is not just another icy moon. It is a captured world from beyond Neptune's orbit, a migrant from the outer dark that somehow ended up in retrograde orbit around a gas giant. And what is happening on its surface should be impossible. By the end of this video, you are going to understand why NASA scientists describe Triton as one of the most exciting targets in the outer solar system, why proposals for return missions have been drafted again and again over the last 30 years, why the data Voyager 2 gathered in those few hours has been reanalyzed more times than almost any other planetary dataset, and why some of the most respected planetary scientists in the world still admit, openly, that they do not know what they are looking at. Before we go any deeper, if you find yourself drawn to the strange and unresolved corners of space science, the kind of questions that no one has yet answered, take a moment to subscribe to the channel and tap the like button. It genuinely helps the work, and it makes it easier to keep producing long-form explorations like this one. Now, let us begin. The story starts in 1846, when the German astronomer Johann Galle confirmed the existence of Neptune by following predictions made by the French mathematician Urbain Le Verrier. Within just 17 days of that discovery, an English brewer and amateur astronomer named William Lassell turned his telescope toward the new planet and saw a faint point of light orbiting it. He had discovered Triton. For the next 143 years, that point of light was all anyone could study. Telescopes improved, photographic plates replaced eyepieces, spectroscopes measured chemical compositions, but no instrument on Earth could resolve any feature on Triton's surface. It remained a dot, just barely brighter than the background stars around it. By the 1970s, astronomers knew Triton was large. They estimated its diameter at around 1,700 miles, making it the 7th largest moon in the solar system. They had carefully measured its orbit, and they had found something that should have been impossible. Triton orbited Neptune backwards. It moved in the opposite direction of Neptune's own rotation. Every other large moon in the solar system orbits in the same direction as its parent planets spin, because they formed together from the same disk of material billions of years ago. A retrograde orbit meant something else entirely. It meant that Triton had not formed with Neptune. It came from somewhere else. This was the first hint that Triton was not what it appeared to be. Scientists began to suspect Triton was a captured object, possibly from the Kuiper Belt, the vast ring of icy bodies that lies beyond Neptune's orbit. If true, that meant Triton was a sibling of Pluto, an outer solar system dwarf planet that had been pulled into Neptune's gravity well, probably violently, billions of years ago. The capture process would have generated enormous tidal heating. It would have torn apart any original moon system Neptune may have had. It would have melted Triton's interior, possibly for hundreds of millions of years. But by 1989, when Voyager 2 was approaching, those ideas were still theoretical. No one had ever seen Triton's surface. No one knew whether there was an atmosphere. No one knew if any heat remained from that ancient capture event, or if Triton had long since frozen into a dead world. The Voyager 2 flyby was the only chance scientists would have in their lifetimes to find out. There were no follow-up missions planned. There still are no missions on the schedule today. Whatever Voyager 2 saw in those few hours would have to last for generations. What it saw was a moon that defied almost every assumption. The atmosphere was real, thin, but present. The surface was young, geologically active in ways no model had predicted. Geysers were erupting in real time, visible in the images as dark plumes rising kilometers into the sky. The terrain showed features no one had ever seen anywhere else, dimpled, cracked, ridged in patterns that resembled the skin of a cantaloupe melon. The polar cap was pink, bright pink, a color that scientists are still arguing about today. And underlying all of it, a quiet possibility that some researchers are taking more seriously every passing year. The possibility that beneath that frozen surface, an ocean of liquid water may still exist, kept warm by tidal forces and radioactive decay, hidden from view, sealed away by miles of ice. Triton was supposed to be a dead end, a frozen relic from the beginning of the solar system. What Voyager 2 detected suggested something else entirely, something active, something dynamic. Something we still do not fully understand. To understand why Voyager 2's Triton flyby mattered so much, you have to understand how little was known before it. For more than a century after Lassell's discovery, Triton existed in the astronomical literature as little more than a number. Orbital period, 5.877 days. Distance from Neptune, roughly 220,000 miles. Apparent magnitude from Earth, around 13.5, far too dim for the naked eye, faint even through most amateur telescopes. There were no maps. There were no photographs of features. There were no measured surface temperatures, no confirmed atmospheric composition, no images of any kind beyond a blurred point of light surrounded by Neptune's faint glow. In 1949, the Dutch-American astronomer Gerard Kuiper, working at the McDonald Observatory in Texas, made a careful study of the Neptunian system and discovered a second moon, a tiny, irregularly shaped object he named Nereid. Nereid was peculiar in its own right. It followed one of the most eccentric orbits of any moon in the solar system, swinging from less than 1 million miles from Neptune to nearly 6 million miles in a single revolution. The discovery of Nereid drew attention back to Triton. If Neptune had two moons that behaved this strangely, what kind of history did this distant planet have? What kind of violence had shaped its system? Through the 1950s and 1960s, astronomers tried to extract whatever information they could from the faint light reflected off Triton's surface. They measured its brightness over time and tried to detect rotation. They studied its color across different wavelengths, looking for chemical signatures. The work was painstaking and frustrating. Every measurement carried huge uncertainties. Some estimates suggested Triton was much larger than it actually turned out to be, possibly even larger than the planet Mercury. Other estimates put it closer to its true size. There were no instruments on Earth capable of settling the question. The first major breakthrough came in 1978. A team led by the American astronomer Dale Cruikshank, working at the Mauna Kea Observatory in Hawaii, used infrared spectroscopy to detect methane on Triton. Methane absorption lines appeared clearly in the spectrum, suggesting that the surface, or possibly a thin atmosphere, contained frozen methane ice. This was significant for two reasons. First, it meant Triton was chemically rich. It was not just a ball of water ice. It had volatiles, compounds that could vaporize at very low temperatures, compounds that could form atmospheres, compounds that suggested geological complexity. Second, methane is a signature of the outer solar system. Inner solar system bodies, like Earth's moon or the rocky planets, do not retain methane on their surfaces. Methane survives only where temperatures are extremely cold and gravity is sufficient to hold it. This finding strengthened the case that Triton had originated in the outer solar system, possibly in the same region where Pluto formed. A few years later, in 1983, the same team detected nitrogen on Triton. This was even more important. Nitrogen is the dominant gas in Earth's atmosphere, but in the outer solar system, nitrogen behaves very differently. At Triton's surface temperatures, nitrogen freezes solid, but it can also exist as a thin gaseous atmosphere, sublimating from solid to gas under the faintest warming. The detection of nitrogen suggested Triton might have an atmosphere, however thin, and that the surface might be covered in nitrogen ice. The question now became urgent. What did Triton actually look like? What was happening on its surface? Was it a static, frozen world, or was something moving down there? The answers would have to wait for Voyager 2. The Voyager mission, originally conceived as a grand tour of the outer planets, had been planning for the Neptune encounter since the early 1970s. Voyager 1 had been sent on a trajectory that took it close to Saturn's moon Titan, sacrificing any chance of visiting Uranus or Neptune. Voyager 2 was the only spacecraft that would reach the ice giants. Its trajectory through Jupiter and Saturn had been carefully designed to leave open the option of continuing to Uranus and then to Neptune, but each gravity assist had to be calculated precisely. A small error at Jupiter could have made the Saturn flyby useless. A small error at Saturn could have made Uranus unreachable. By the time Voyager 2 reached Uranus in January 1986, the spacecraft was already operating well beyond its original 5-year mission lifetime, and engineers had been quietly working on software patches and contingency plans to keep it functional for another 4 years. The Neptune encounter required a difficult decision. The mission planners wanted to study Neptune's atmosphere closely, but they also wanted to get the best possible view of Triton. The two goals were in tension. To get close to Triton, Voyager 2 would have to pass over Neptune's north pole at a very specific angle, threading a narrow trajectory window that would slingshot the spacecraft toward its largest moon. This trajectory carried Voyager 2 within 3,000 miles of Neptune's cloud tops, the closest approach to any planet of the entire mission. It also meant that after the Triton flyby, Voyager 2 would be flung southward, below the plane of the solar system, on a path that guaranteed it would never encounter another planet again. The team made the call. They prioritized Triton. They knew this was the only chance. In the months leading up to the encounter, anticipation built at the Jet Propulsion Laboratory in Pasadena. The science team gathered around monitors. Engineers double-checked every command sequence. The Deep Space Network was prepared to receive data from a spacecraft now so far from Earth that signals took more than 4 hours each way. Voyager 2 had been traveling for so long that several of the original mission scientists had retired, and a new generation had taken their places. Bradford Smith, the leader of the imaging team, prepared press briefings. Ede Stone, the project scientist who had been with the mission since before launch, fielded questions from reporters about what the spacecraft might see. No one quite knew what to expect. The best ground-based images of Triton showed a featureless disk. Theoretical models suggested it might look like Earth's moon, grey and heavily cratered. Other models suggested it might resemble Saturn's moon Iapetus, with bright and dark hemispheres. A few researchers suggested it might be geologically interesting, perhaps with some kind of resurfacing activity. Almost no one predicted what Voyager 2 was actually about to find. On August 24, 1989, Voyager 2 passed Neptune. A few hours later, it began its closest approach to Triton. The cameras were already returning images. The instruments were measuring magnetic fields, temperatures, particle environments, atmospheric composition. The data flowed back across nearly 3 billion miles, arriving at Earth more than 4 hours later, line by line, image by image. And as those images began to appear on the monitors at JPL, the scientists stopped talking. They stared at the screens. Then they began to argue. Then they began to shout. Because what Voyager 2 was showing them was not a dead moon. It was something else entirely. Something none of them had been trained to interpret. To understand the shock of what Voyager 2 was sending back, you have to understand what the scientific community genuinely believed about Triton in the days before the encounter. The predictions were not random guesses. They were the product of decades of theoretical work, of careful modeling, of cautious extrapolation from what was known about other icy bodies in the solar system. And almost all of them turned out to be wrong. The dominant view in the 1980s held that Triton would resemble a slightly larger, slightly more interesting version of Jupiter's moon Callisto. Callisto is heavily cratered, geologically dead, its surface essentially unchanged for billions of years. It is the kind of world that planetary scientists call a primitive body. It froze early in solar system history and never thawed. Most researchers expected Triton to look similar, a dark, ancient surface saturated with impact craters. Perhaps some faint surface features, perhaps a few large basins, but fundamentally, a relic from the early solar system, preserved exactly as it had been since the era of heavy bombardment 4 billion years ago. This expectation was built on a chain of reasonable assumptions. Triton was far from the sun, far from any significant heat source. It was small enough that any internal heat from its formation should have radiated away to space long ago. Its surface temperatures were so cold that water ice would behave like rock, brittle and inert. There was no obvious mechanism to drive geological activity. No nearby massive planet to flex its interior with tidal forces the way Jupiter does to Io. No recent collision to inject fresh energy. No molten core that could plausibly remain liquid for billions of years in such a small body. There were dissenting voices. A handful of researchers had pointed out that if Triton was indeed a captured object, the capture process itself would have generated tremendous tidal heating. Some calculations suggested that the energy released during capture could have melted Triton entirely, turning it into a global ocean of liquid water for tens of millions of years. If that were true, then Triton would have started its life around Neptune as a hot, fully differentiated body, with a rocky core, a liquid mantle, and an icy crust slowly forming on the surface. But these were considered fringe ideas. Most scientists believed that whatever ancient activity might have occurred, it had ended billions of years ago. By 1989, Triton should have been thoroughly, completely frozen. The expected atmospheric composition was equally conservative. Methane and nitrogen had been detected from Earth, but most models predicted only an extremely tenuous atmosphere, perhaps a few microbars of pressure, essentially a vacuum by Earth standards. The atmosphere was expected to be uniform, stable, possibly so thin that it would be barely detectable even from up close. There were no predictions of weather, no predictions of seasonal variation, no predictions of clouds, hazes, or any other dynamic atmospheric phenomena. The atmosphere, if it existed at all, was assumed to be a passive byproduct of slow sublimation from surface ices, with no significant exchange of mass between the surface and the gas envelope. Surface composition was expected to be mostly water ice, some methane ice, possibly some nitrogen ice in certain regions. The colors would be muted, grayish, perhaps with some faint brownish tints from organic compounds slowly produced by cosmic ray bombardment over billions of years. Nothing dramatic, nothing colorful, nothing that would distinguish Triton meaningfully from the other large icy moons that Voyager 2 had already photographed at Jupiter, Saturn, and Uranus. Even the size estimates were uncertain. Some calculations suggested Triton might be larger than Earth's moon. Others put it smaller. Without resolved images, there was no way to measure the diameter precisely. The diameter could only be inferred from brightness, and brightness depended on assumptions about how reflective the surface was. If Triton was very bright, like fresh snow, then it could be relatively small while still appearing as bright as it did from Earth. If it was dark, like charcoal, it would have to be much larger to reach the same brightness. The actual answer would not be known until Voyager 2 could measure the disk directly. There was one prediction that did not turn out to be wrong, and it was perhaps the most important one. Triton's retrograde orbit was unambiguous. No model could explain it through any natural formation process. The orbital mechanics of planetary systems make it virtually impossible for a moon to form in the same disk as its parent planet, and end up orbiting in the opposite direction. Computer simulations consistently showed that retrograde moons must be captured. They cannot form in place, so scientists were confident that Triton had originated somewhere else, probably in the region of the solar system beyond Neptune's orbit, in the same general zone where Pluto and the rest of the Kuiper Belt objects had formed. This had profound implications. If Triton was a captured Kuiper Belt object, then it represented a unique opportunity. The Kuiper Belt was, in 1989, still mostly theoretical. Pluto had been discovered in 1930, but it would not be until 1992 that astronomers confirmed the existence of a second Kuiper Belt object. Today, we know of thousands of them, with population estimates running into the hundreds of thousands of bodies larger than 60 miles across. But in the summer of 1989, Triton was potentially the only large Kuiper Belt-type object that humanity would ever get to see up close in the foreseeable future. Studying it meant studying, by proxy, an entire population of objects that had remained essentially untouched since the formation of the solar system. The expectations were modest, but the stakes were high. Even if Triton turned out to be geologically dead, even if its atmosphere was barely detectable, even if its surface was just another cratered icy plain, the data would still be invaluable. Scientists would still get composition measurements. They would still get magnetic field data. They would still get the first close-up view of an outer solar system body of this size. And if Triton happened to be more interesting than expected, even a little more interesting, that would be a bonus that nobody dared to count on. There was one more reason for caution in the predictions. The Voyager 2 spacecraft was now operating at the absolute limits of its design. Its cameras had been built for the brightness levels of Jupiter, where sunlight is about 4% of what it is at Earth. At Neptune, sunlight is about 0.1% of what it is at Earth. The cameras would need extremely long exposures, and during those exposures, the spacecraft would have to track its target with absolute precision. Any vibration, any small rotation, any thermal disturbance could blur the images beyond usefulness. The team had developed a technique called image motion compensation, in which the entire spacecraft would slowly rotate during the exposure to follow Triton across the field of view. It had never been used at full scale before. There was no guarantee it would work. Add to this the communication challenges. Data rates from Voyager 2 at Neptune were a small fraction of what they had been at Jupiter. The deep space network had been upgraded, antennas linked together, signal processing improved, but the spacecraft's transmitter was still only 23 watts. By the time the signal reached Earth, it was almost unimaginably faint. Every bit of data was precious. Every image was the result of careful engineering and even more careful luck. Scientists were prepared to be patient. They were prepared to be disappointed. What they were not prepared for was Triton itself. The first hints that something was wrong with the expectations came before the closest approach. As Voyager 2 raced toward Triton, the resolution of its images steadily improved. What had begun as a featureless disk slowly resolved into something with structure, with contrast, with detail. And the details did not match the predictions. The first thing the imaging team noticed was the color. Triton was not gray. It was not the muted, dusty tone that had been expected for a primitive icy body. Parts of it were genuinely, vividly pink. The southern polar cap glowed with a salmon-colored brightness that nobody on the science team had a ready explanation for. The northern regions were darker, but they too showed unexpected coloration, with patches of red, orange, and ochre interspersed with brighter terrain. The surface had personality. It looked alive in a way that frozen worlds are not supposed to look. Bradford Smith, leading the imaging team, recalled in later interviews that there was an uncomfortable silence when the first color-corrected images appeared on the monitors. Nobody quite knew what to say. The colors implied chemistry. The chemistry implied processing. The processing implied energy. And energy was the one thing Triton was not supposed to have. The second thing they noticed was the cratering, or rather the lack of it. Voyager 2 had photographed Callisto, Rhea, Mimas, Tethys, Umbriel, and dozens of other icy moons across the outer solar system. All of them showed dense populations of impact craters. The crater counts were so consistent across these bodies that planetary scientists had developed standardized techniques for estimating surface ages based on crater density. The more craters per unit area, the older the surface. Some of the moons Voyager had visited showed surfaces that had been essentially undisturbed for 4 billion years. Their crater populations were saturated, meaning that any new impact would simply overlap an existing crater. Triton was different. The craters were sparse. In some regions, they were almost absent. The surface looked young, not just somewhat younger than expected, but dramatically younger. Initial estimates suggested some regions of Triton might be less than 100 million years old, which is essentially yesterday on geological timescales. Some smaller regions might be only a few million years old, or even less. For a moon that was supposed to have frozen solid billions of years ago, this was an extraordinary finding. Something had been resurfacing Triton, erasing the impact record, smoothing over the geological scars. And whatever it had been doing it recently. The third surprise was the topography. As the resolution improved, the surface began to show features unlike anything seen elsewhere in the solar system. Across vast regions of the equatorial zone, the terrain was dimpled and ridged in a pattern that quickly earned the informal name cantaloupe terrain. The name came from the resemblance to the rough, netted skin of a cantaloupe melon. The dimples were roughly circular depressions, perhaps 20 to 30 kilometers across, separated by ridges that formed a polygonal network across the surface. Nothing like it had been seen on any other moon. Nothing like it had been predicted. Nothing in the planetary science literature offered a clear mechanism for producing such a pattern. Theories were proposed almost immediately. Some researchers suggested the cantaloupe terrain was the result of diapirism, a process in which less dense material rises through denser overlying material in a slow, viscous flow. In this model, blobs of warmer ice or other materials would have risen toward the surface, creating bulges that eventually collapsed into the dimpled pattern. Others suggested the terrain might be the result of repeated cycles of partial melting and refreezing, with each cycle slightly altering the surface texture. Still, others proposed that the cantaloupe pattern was the relic of some ancient process that no longer operates, perhaps a process related to the violent capture of Triton billions of years ago. None of these explanations was fully satisfying. None of them could account for all the observed features. The cantaloupe terrain remains, decades later, one of the most enigmatic landscapes in the solar system. Then came the polar cap. The southern hemisphere of Triton, which happened to be facing the sun during the Voyager 2 encounter, was covered by a vast, bright deposit. The cap extended from the South Pole to roughly the equator, dominating an entire hemisphere of the moon. Its color was that distinctive pink, the salmon tone that had startled the team. Its composition, inferred from spectroscopy, was primarily nitrogen ice, with some methane and possibly other frozen volatiles mixed in. The cap was bright. It reflected a remarkable fraction of the incoming sunlight, which made Triton one of the most reflective bodies in the solar system. The albedo, the technical term for reflectivity, was measured at around 0.7 in some regions, comparable to fresh snow on Earth. A surface that bright in such a cold environment should have been stable. Sunlight should have had almost no effect. The cap should have been changeless, frozen, immobile. But the data showed something else. Across the polar cap, Voyager 2 began to detect dark streaks. They were thin, elongated features, almost like wind-blown smears, stretching for tens or hundreds of kilometers across the bright nitrogen surface, and every single one of them was pointing the same direction. Northeast, without exception. The streaks were aligned with what appeared to be the prevailing surface winds, suggesting that something was being deposited on the cap and then carried by an atmospheric flow. This was strange enough on its own, but the team also noticed that the streaks had clear starting points. Each streak began at a distinct dark spot on the surface, a kind of focal point from which the dark material seemed to emanate. The spots were small, perhaps a few kilometers across. The streaks extended away from them in long fans, narrowing in width with distance. Whatever was producing these features was active. Something was depositing dark material onto the surface, and the wind was carrying it across the cap. Then, almost by accident, the team found the source. During one of the imaging sequences, an alert engineer noticed an unusual feature on the limb of Triton, the curved edge of the moon as seen against the black background of space. It looked like a small protrusion, an irregularity in what should have been a smooth horizon. The engineer flagged it for closer examination. When the science team studied the image, they realized they were looking at a plume. A column of dark material rising from the surface, climbing several kilometers into the thin atmosphere, then bending over and trailing downwind for a great distance, possibly more than 100 kilometers. They examined other images. They found more plumes. By the end of the encounter, they had identified at least 2 active plumes erupting from Triton's surface, with possible evidence of several more. These were geysers, active geysers, on a moon supposedly frozen solid. At surface temperatures of -391 degrees Fahrenheit, erupting in real time in front of a spacecraft that had traveled 12 years and 3 billion miles to witness them. The shock at the Jet Propulsion Laboratory was something the senior scientists would describe for the rest of their careers. They had expected a dead world. They had found one that was breathing. The plumes raised an immediate and urgent question. What was driving them? A geyser needs energy. Energy at -391 degrees Fahrenheit is not supposed to exist on a body the size of Triton. There should be no internal heat sufficient to drive eruptions. There should be no liquid reservoir to feed them. There should be no pressure mechanism to launch material kilometers into the sky. And yet here they were, multiple plumes, all aligned with the same wind direction, all erupting on a world that according to every model should have been geologically inert. The discovery would consume planetary scientists for the next 3.5 decades, and in 2026, the explanation for those plumes is still not settled. To understand how Voyager 2 was able to detect the plumes, the cantaloupe terrain, the polar cap, and the atmospheric streaks of Triton, you have to step back and look at the instruments themselves. Because what the spacecraft accomplished during those few hours in August 1989 was not just a scientific triumph. It was an engineering miracle. The technology that made the discoveries possible was already, by 1989, more than 15 years old. By the standards of consumer electronics, it was prehistoric. By the standards of modern space exploration, it was almost laughably primitive, and yet it worked. It worked at the absolute edge of its capabilities, in the coldest, darkest environment any human-made machine had ever operated in, and it returned data that scientists are still analyzing today. The imaging system that captured the famous Triton photographs consisted of 2 cameras mounted on a movable scan platform attached to one side of the spacecraft. The narrow-angle camera had a focal length of 1,500 millimeters and a small field of view designed for high-resolution images of distant targets. The wide-angle camera had a focal length of 200 millimeters, designed for broader landscape views. Both cameras used Vidicon tubes, an analog imaging technology that predated the charge-coupled devices used in modern digital cameras. A Vidicon tube works by scanning an electron beam across a photoconductive target. The light from the scene falls on the target, changes its electrical properties, and the scanning beam reads out the resulting pattern as a video signal. The signal is then digitized, compressed, and transmitted back to Earth. The Vidicon system was designed in the early 1970s, and by 1989, it was an antique. The cameras produced images that were 800 pixels by 800 pixels in resolution, a tiny fraction of what even a basic smartphone camera produces today. Each image was stored as raw data on the spacecraft's onboard tape recorder, a device that resembled an oversized cassette tape player. The tape recorder had a total capacity of about 100 minutes of data, after which it had to be played back to Earth before new data could be written. This meant that the Voyager 2 team had to plan every single image exposure with extraordinary care, balancing the desire for more pictures against the limited recording capacity. At Neptune and Triton, the imaging challenge was exponentially worse than it had been at Jupiter. Sunlight at Triton is roughly 900 times weaker than sunlight at Earth. The cameras required exposure times measured in seconds rather than the fractions of a second used at Jupiter. During those long exposures, the spacecraft was moving at more than 40,000 miles per hour relative to its target. Without compensation, every image would have been a smeared blur. The solution was the image motion compensation technique mentioned earlier. The entire spacecraft, weighing more than 1,800 pounds, had to rotate slowly during each exposure, tracking Triton across the field of view with a precision measured in fractions of a degree per second. The rotation was controlled by tiny hydrazine thrusters, firing in carefully calculated pulses. Any error in timing or thrust would have ruined the image. Beyond the cameras, Voyager 2 carried a suite of instruments that together provided a remarkably complete picture of any body it encountered. The infrared interferometer spectrometer, known as IRIS, measured thermal emission from surfaces and atmospheres, allowing temperatures to be calculated and atmospheric composition to be inferred. The ultraviolet spectrometer measured emissions in the far ultraviolet, providing information about the upper atmospheres of planets and moons. The photopolarimeter measured the brightness and polarization of reflected light, which could reveal surface textures and the sizes of particles in atmospheres or rings. The magnetometer measured magnetic fields, both the steady fields of planets and the fluctuating fields of plasma environments. The plasma science instrument, the low-energy charged particle detector, and the cosmic ray subsystem together measured the particles and radiation environments around each body Voyager visited. At Triton, several of these instruments worked together to produce the integrated picture that emerged from the encounter. IRIS measured the surface temperatures, confirming the -391 degrees Fahrenheit value and revealing slight variations across different regions. The ultraviolet spectrometer detected the thin atmosphere, characterizing it as primarily nitrogen with traces of methane and other compounds. The photopolarimeter studied the polar cap and inferred the size and nature of the particles on its surface. The magnetometer searched for any sign of an intrinsic magnetic field around Triton and found nothing, suggesting that whatever interior structure the moon possessed did not include a convecting metallic core. The spacecraft itself was built around a 12-foot-tall, 1,820-pound structure dominated by a large parabolic high-gain antenna. The antenna pointed back toward Earth throughout the encounter, allowing Voyager 2 to transmit data while simultaneously performing science observations. Power came from 3 radioisotope thermoelectric generators mounted on a boom extending away from the main body of the spacecraft. By 1989, these generators were already producing significantly less power than they had at launch. The plutonium-238 had been decaying for 12 years. Engineers had been managing the declining power budget carefully, shutting down systems that were not needed, lowering the heater settings on certain instruments, accepting reduced data rates to save energy. Every watt counted. Communication with Voyager 2 at Neptune required upgrades to the deep space network. The signal arriving at Earth from Triton was extraordinarily faint, roughly 1 quintillionth of a watt, far below what the existing antennas could detect reliably. To handle the encounter, engineers electronically linked multiple antennas together, combining their signals to improve sensitivity. The 230-foot antennas in Goldstone, California, were linked with the smaller 113-foot antennas at the Very Large Array Radio Telescope in New Mexico. In Australia, the antennas at Canberra were linked with the radio telescope at Parkes. The combined signal-collecting area was much larger than any single antenna could provide. Even with these upgrades, the data rate from Voyager 2 at Neptune was only about 21,600 bits per second, slow by any standard, but enough to return the scientific bounty of the encounter. The data flowed back in a continuous stream during the encounter and for weeks afterward. Each image required several minutes to transmit. Each spectroscopic measurement, each magnetometer reading, each particle count had to be carefully packaged and queued for transmission. The spacecraft's onboard computer, the Flight Data Subsystem, managed the entire process. The computer had a total memory of about 4,096 18-bit words, equivalent to less than 9 kilobytes by modern measures. Modern smartphones have memory capacities millions of times larger. Yet this small computer flawlessly orchestrated one of the most complex scientific operations ever attempted in deep space. What makes the Triton observations particularly remarkable is that they were essentially a one-time opportunity. Voyager 2's trajectory through the Neptunian system meant that the close approach to Triton lasted only a few hours. During that window, the spacecraft had to acquire and image multiple targets, perform spectroscopic measurements at different geometries, monitor the plasma environment, and execute all the planned observations within a strict timeline. There were no second chances. If a sequence failed, if a command was missed, if an instrument malfunctioned at the wrong moment, the data would simply be lost forever. There would be no return mission. There would be no follow-up. The Voyager 2 flyby was, and remains, the only close-up examination of Triton that humanity has ever conducted. This is part of why the Triton dataset continues to be reanalyzed even now, more than 3 decades later. Modern image processing techniques can extract details from the Voyager images that the original team did not have the computational power to recover. Modern spectroscopic methods can interpret the iris and ultraviolet data in new ways. Modern modeling techniques can integrate the measurements with new physical theories that have emerged since 1989. Every few years, a new analysis of old Voyager data produces a new insight about Triton. The encounter that lasted a few hours continues to yield discoveries decades after the spacecraft has departed. And the discoveries that came directly from those hours, the ones the team began to piece together as the data was still arriving, would form the foundation of every theory about Triton that has been proposed since. The plumes, the polar cap, the cantaloupe terrain, the thin atmosphere, the strange retrograde orbit, the geological youth, each one demanded an explanation. Each one resisted easy answers. And the first of those discoveries, the one that started the cascade of revelations, would shake the foundations of how scientists thought about icy moons. The first major discovery, the one that announced itself before any of the others were fully understood, was the existence of the geyser plumes themselves. They were spotted in the imaging data within hours of closest approach, and they immediately became the headline finding of the entire Neptune encounter. The press conferences at the Jet Propulsion Laboratory in the days following August 25, 1989, were dominated by images of these dark columns rising from Triton's surface, captured in the slanting sunlight of a polar summer, casting long shadows across the bright nitrogen ice. The first plume was identified by the imaging team in a sequence of high-resolution photographs of the South Polar region. It appeared as a narrow vertical column rising from a small dark spot on the surface, climbing roughly 5 miles into the thin atmosphere, then abruptly bending and trailing horizontally for approximately 90 miles downwind. The bend was sharp, almost angular, suggesting that the plume reached a layer of the atmosphere where vertical motion stopped and horizontal flow took over. The geometry implied an atmospheric structure with distinct layers, a kind of inversion that prevented the plume material from rising higher. The second plume was found shortly afterward in a different region of the polar cap. Its appearance was similar: a vertical column, a sharp bend, a long horizontal trail. The two plumes were separated by hundreds of miles, but their trails pointed in the same general direction. Whatever was driving the wind that bent the plumes was operating across the entire polar region, organizing the deposition of material onto the cap in a consistent pattern. The scientific reaction was immediate and intense. Active geological processes on a body as cold and small as Triton were not predicted by any standard model. The energy budget did not add up. A geyser requires a source of heat sufficient to vaporize or pressurize a working fluid, and Triton's surface temperature of -391 degrees Fahrenheit suggested that any internal heat was either non-existent or trapped so deeply that it should have no effect on the surface. Yet there they were, multiple plumes, erupting in real time, visible to the cameras of a passing spacecraft. The first explanation proposed was a solar-driven mechanism, sometimes called the solid-state greenhouse model. The idea was that Triton's polar cap, although extremely cold at the surface, might allow sunlight to penetrate a short distance into the translucent nitrogen ice. Beneath the surface, the trapped solar energy could slowly warm a layer of nitrogen, raising its temperature by just a few degrees above the surrounding ice. At those temperatures, even small increases would dramatically increase the vapor pressure of nitrogen. The gas would accumulate beneath an overlying layer of darker, less translucent material. The pressure would build over time. Eventually, the overlying layer would rupture. The trapped nitrogen gas would burst out in a sudden eruption, carrying entrained dark particles into the atmosphere. This model had several attractive features. It required no internal heat source. It used only the small amount of solar energy reaching Triton's surface. It naturally explained why the plumes were concentrated in the polar region, where the sun was currently shining most directly. It also explained the dark material in the plumes, which could plausibly be composed of complex organic compounds called tholins, produced by the action of ultraviolet radiation and cosmic rays on methane and nitrogen ices over geological time. These tholins, accumulated in a thin layer just beneath the surface, will be lofted into the atmosphere by the eruption. A competing model proposed an internal heat source. In this view, the plumes were powered by warmth from deeper within Triton, perhaps residual heat from the moon's violent capture by Neptune billions of years ago, perhaps heat generated by ongoing radioactive decay in a rocky core, perhaps tidal heating from the gravitational interaction with Neptune. The internal heat would warm pockets of nitrogen or other volatiles beneath the surface, and the resulting pressurized gas would find weaknesses in the overlying ice and erupt outward. The two models made different predictions. The solar-driven model predicted that the plumes should be concentrated in the sunlit polar regions and should shut down or migrate as Triton's seasons changed. The internal heat model predicted that plumes could appear anywhere on the surface, regardless of solar illumination, and should persist over much longer time scales. The Voyager 2 data, while clearly showing plumes in the sunlit South Polar region, could not definitively distinguish between the two models. The encounter was simply too brief. The spacecraft could not return to observe whether the plumes persisted, whether new plumes appeared in different regions, whether their distribution changed over time. The data offered a snapshot. The interpretation required extrapolation, and extrapolation could go in multiple directions. What was certain, regardless of the mechanism, was that the plumes were depositing material on Triton's surface. The dark streaks across the polar cap, all aligned northeast, were the visible record of past eruptions. Each streak began at a focal point that probably marked the location of an active or recently active vent. The wind carried the dark particles from the vent in a consistent direction, depositing them across the bright nitrogen ice in long, narrow trails. Counting the streaks gave a rough estimate of the number of eruption sites. The team identified more than 100 of them, though the true number was probably higher, with many smaller features below the resolution limit of the cameras. The discovery of active geysers immediately changed the way planetary scientists thought about Triton. The moon was no longer a frozen relic. It was a dynamic world, with ongoing processes, with energy flow between the interior and the surface, with material being transporting, deposited, and possibly recycled. The geological youth of the surface, evidenced by the sparse cratering, suddenly made more sense. If plumes had been depositing material across the polar cap for hundreds of millions of years, and if similar processes had operated elsewhere on the moon, then much of the surface could have been resurfaced repeatedly during Triton's history. The crater record was not missing because impacts had been rare. It was missing because the impacts had been covered, buried, erased by the slow accumulation of fresh material from below. The wind that bent the plumes raised additional questions. A wind requires an atmosphere with significant mass, or at least with significant flow. The thin atmosphere of Triton, with surface pressure of only about 14 microbars, less than 100,000th of Earth's atmospheric pressure, should not be able to sustain a strong wind. Yet the consistent alignment of the plume trails and the surface streaks indicated that something was moving the air in an organized way. Models of Triton's atmospheric dynamics, developed after the Voyager 2 encounter, suggested that the wind was driven by sublimation. As nitrogen ice sublimated from the warmer parts of the polar cap and recondensed in the colder, shaded regions, the resulting mass flow created a measurable atmospheric circulation. The winds were not strong by Earth standards, perhaps only 10 to 30 feet per second, but in such a thin atmosphere they were enough to carry the lighter plume particles for great distances. The discovery of the plumes also forced a reconsideration of the broader category of icy moons. If Triton, in the cold outer reaches of the solar system, could host active geological activity, then perhaps other icy moons were not as dead as they appeared. The Galileo mission to Jupiter, which arrived in 1995, would eventually confirm subsurface oceans on Europa and active geological processes on other Jovian moons. The Cassini mission to Saturn would discover, in 2005, that the small moon Enceladus was venting plumes of water vapor and ice particles from its south polar region, plumes that bear a striking resemblance to those seen on Triton. Each of these later discoveries traced its intellectual lineage back to Triton. The Voyager 2 finding was the first crack in the assumption that small, cold, distant bodies are uninteresting. Once that assumption was broken, an entire category of worlds opened up for serious scientific investigation. But the plumes were only the first of the major revelations. The data continued to flow back from Voyager 2 in the weeks following the encounter, and as the science teams worked through the images and measurements, they began to find more anomalies. The next discovery would push the strangeness of Triton even further, suggesting that beneath the frozen surface, something even more remarkable might be waiting. The second major discovery emerged more slowly than the first. It did not announce itself in a single dramatic image. It was assembled over months and years of careful analysis, piece by piece, from the data Voyager 2 had collected during those few hours of close approach. And when it finally came into focus, it changed everything about how scientists understood Triton's interior. The discovery was that Triton, beneath its frozen surface, might still harbor a global ocean of liquid water. The first clues came from the density measurement. By tracking Voyager 2's trajectory as it passed through the Neptunian system, the navigation team was able to determine the gravitational pull of every major body the spacecraft encountered. From the curvature of the trajectory near Triton, combined with the precise measurement of the moon's diameter from imaging, the team calculated Triton's average density. The result was approximately 2.06 grams per cubic centimeter, significantly higher than the density of pure water ice, and substantially higher than the densities measured for most of the icy moons of Saturn and Uranus. This density implied that Triton was not a simple ball of frozen volatiles. It had to contain a substantial amount of rocky material, perhaps as much as 65 to 70% rock by mass, with the rest being water ice and other volatiles. A body with that much rock has implications. Rock contains radioactive isotopes, primarily uranium, thorium, and potassium, which decay slowly over billions of years and release heat as they do so. The amount of radiogenic heat produced by Triton's rocky component, when integrated over the age of the solar system, is enormous. Some calculations suggest that if all that heat were trapped inside the moon, it would be more than sufficient to maintain a global liquid water ocean indefinitely. The only question was whether the heat could actually be retained, or whether it would escape to the surface and radiate away to space. The retention of internal heat depends on the thermal properties of the overlying ice. Water ice is a relatively poor conductor of heat. A thick ice shell can act as an insulating blanket, slowing the loss of internal warmth and allowing the deeper layers to remain warm enough for liquid water to persist. Calculations performed in the years following the Voyager 2 encounter, using the density and surface temperature measurements as constraints, suggested that Triton's ice shell could be tens of miles thick, perhaps as much as 100 miles thick in some regions, with a liquid water ocean beneath it that could be hundreds of miles deep. The ocean would be in contact with the rocky core below, providing a chemically active environment in which various reactions could occur over geological time. This was an extraordinary possibility. A subsurface ocean on Triton would mean that one of the coldest, most distant worlds in the solar system could host a liquid water environment. Liquid water, on Earth, is the universal solvent for life. Every known living organism depends on it. The discovery of subsurface oceans on other worlds had become, by the time of the Voyager 2 encounter, one of the central preoccupations of planetary science, because such oceans are among the most promising candidates for environments where extraterrestrial life might exist. Europa, around Jupiter, had been suspected of harboring such an ocean since the Voyager flybys of the late 1970s, and the suspicion would be strengthened dramatically by the Galileo mission in the following decade. Enceladus, around Saturn, would join the list after the Cassini observations of the mid-2000s. And Triton, with its high density, its active geology, and its history of violent capture, became a candidate as well, even though the evidence was less direct than for the other two. The capture history is central to the case for a Triton ocean. When Triton was captured by Neptune billions of years ago, the process would have generated tremendous tidal heating. The orbit immediately after capture would have been highly elliptical, swinging Triton close to Neptune at one point and far away at another. On each orbit, the gravitational tides from Neptune would have flexed Triton's interior, generating heat through internal friction. Calculations suggest that this tidal heating could have been intense enough to melt Triton almost entirely, creating a temporary global ocean that extended from near the surface to the rocky core. The tidal heating would have lasted as long as the orbit remained eccentric, possibly for hundreds of millions of years, during which time the dissipation of energy in Triton's interior would have gradually circularized the orbit. Today, Triton's orbit is almost perfectly circular. The tidal heating has long since diminished to negligible levels. The orbit is also retrograde, with Triton moving in the opposite direction of Neptune's rotation, which means that tidal forces actually pull Triton slowly inward toward the planet rather than pushing it outward, as is the case for most prograde moons. Over the next few billion years, Triton will spiral closer to Neptune, and eventually it will either collide with the planet or be torn apart by gravitational tides, forming a spectacular ring system. But that is the distant future. For now, the orbit is stable enough, and the tidal heating from the current configuration is too weak to have a significant effect on the interior. If a subsurface ocean exists on Triton today, it must be sustained by some combination of radiogenic heat from the rocky core and residual heat from the ancient capture event. The combination is plausible. Heat from radioactive decay in a body of Triton's size could maintain a liquid water layer for the entire age of the solar system, provided the overlying ice shell is thick enough to act as an effective insulator. The capture heat, while no longer the dominant contribution, would have set the initial thermal state of the moon, ensuring that an ocean formed in the first place. Once a liquid layer is established, it tends to persist because the thermal gradient through the ice shell maintains a stable configuration with the warmest material at the bottom and the coldest at the surface. The evidence for the ocean is, however, indirect. The Voyager 2 magnetometer did not detect any intrinsic magnetic field around Triton, and it did not have the sensitivity or the proximity to detect the kind of induced magnetic signature that revealed the Europa Ocean during the Galileo mission. The plumes seen at the polar cap are not necessarily evidence of an ocean. They could be driven by solar heating of near-surface nitrogen ice, with no involvement from any deeper liquid layer. The cantaloupe terrain might be the result of solid-state convection in the ice shell, again not requiring any liquid water beneath. Every observable feature can be explained, in principle, without invoking an ocean. The case for the ocean rests on theoretical modeling, on the density measurement, and on analogy with other icy moons that have stronger evidence for subsurface liquids. Still, the case is strong enough that many planetary scientists treat the Triton Ocean as a serious possibility. In the years since the Voyager 2 encounter, multiple research groups have published modeling studies that conclude an ocean is consistent with the available data. Some studies have explored what such an ocean might be like chemically. The water would not be pure. It would be in contact with the rocky core, dissolving salts and other compounds over billions of years. The salinity might be high, comparable to the most saline seas on Earth. The water might also contain ammonia, which acts as an antifreeze and lowers the freezing point. An ammonia-water mixture could remain liquid at temperatures significantly below the freezing point of pure water, making it easier for the ocean to persist in Triton's cold interior. Other studies have explored what kinds of chemistry might occur at the interface between the ocean and the rocky core. Hydrothermal activity, similar to that seen at deep-sea vents on Earth, might be possible if any heat is being released from the core. Such activity could drive a rich chemistry, producing a variety of organic and inorganic compounds. The ocean, if it exists, is sealed away beneath miles of ice. There is no direct way to observe it from outside. The plumes do not reach down to it. The geology of the surface does not provide any windows into it. The magnetometer signature, if it could be measured by a future orbiter, might confirm its existence through the induced electrical conductivity of the salty water responding to Neptune's magnetic field. But no such orbiter exists. None is scheduled. The question of whether Triton has an ocean remains open more than 3 decades after the Voyager 2 encounter raised it, and there is no near-term prospect of an answer. The pattern was beginning to emerge from the data. Each new finding pointed in the same direction. Triton was more active, more complex, more alive in geological terms than anyone had expected, and the next discovery would deepen the pattern even further. The third major discovery to emerge from the Voyager 2 data was the recognition that Triton's surface, far from being a static record of ancient impacts, was a dynamic landscape in active and recent transformation. Each new region the images revealed showed terrain that had no clear analog elsewhere in the solar system. The cantaloupe terrain was the first to catch the eye, but it was only one of several puzzling landscape types that covered the moon. As the imaging team worked through the data in the months after the encounter, they began to map Triton in detail, and the patterns that emerged suggested a world where ice behaved in ways that scientists had not anticipated. The cantaloupe terrain, which occupied much of the equatorial region in the imaged hemisphere, was characterized by closely spaced depressions of remarkably uniform size and shape. Each depression was roughly 20 to 30 kilometers across, almost circular, but with subtle polygonal edges where adjacent depressions met. The depressions were separated by raised ridges that formed an interconnected network across the surface. The overall effect was strikingly regular, almost geometric, as if some process had imposed a characteristic length scale on the entire landscape. Nothing about the appearance suggested impact origin. The depressions were too uniform, too closely packed, too lacking in the radial structure that marks genuine impact craters. There was something else, and the mechanism that produced them was not obvious from the images alone. The leading hypothesis, developed in the years following the encounter, was that the cantaloupe terrain formed through a process called diapirism. In this view, the icy crust of Triton contained pockets of lower density material that, over geological time, rose slowly toward the surface through the denser surrounding ice. The rising material would not necessarily be liquid. It could be a slightly warmer, slightly less dense form of ice that flowed sluggishly upward through the colder, denser overlying material. As the diapirs reached the surface, they would create the dimpled depressions seen in the images. The polygonal pattern would emerge naturally from the close packing of multiple diapirs across the landscape. For this model to work, Triton's ice shell would need to contain compositional or thermal variations large enough to drive the rising motion. The leading candidate for the lower density material was a mixture of water ice with ammonia or methane, which would have a slightly lower density than pure water ice and would flow more readily at low temperatures. If such mixtures existed in pockets within the shell, the difference in density would be sufficient to drive diapirism over geological time. The model predicts that the cantaloupe terrain represents a late stage in the moon's geological evolution, when the upper part of the ice shell had cooled enough to allow diapirs to rise and stall near the surface, creating the characteristic pattern of depressions. Other regions of Triton showed entirely different landscapes. There were vast smooth plains, called by the planetary scientists the cantaloupe terrane's neighbors, but distinct in their texture. These plains lacked the dimpled appearance and instead presented broad, gently undulating surfaces with few features at the resolution of the images. The smoothness suggested that these regions had been resurfaced by the deposition of fresh material, possibly the same kind of material that the plumes were depositing on the polar cap. If similar volcanic or cryovolcanic activity had operated across the Moon in the geologically recent past, the smooth plains could be the relics of that activity, frozen lakes or flows of nitrogen, methane, or water-based mixtures that had erupted onto the surface and solidified. The presence of cryovolcanism on Triton has become one of the most discussed topics in the planetary science literature on the Moon. Cryovolcanism refers to volcanic activity in which the working fluid is not molten rock, as on Earth, but a mixture of frozen volatiles that has been warmed enough to flow. On Triton, the candidate fluids include water mixed with ammonia, methane, nitrogen, and possibly other compounds. The eruption of such mixtures onto the surface would produce flows that look superficially like volcanic features on Earth, with channels, lobate margins, and broad fan-shaped deposits, but the temperatures involved would be far lower. A cryovolcanic flow on Triton might erupt at temperatures only slightly above the surrounding surface, perhaps -200 or -250 degrees Fahrenheit, still cold enough to feel impossibly frigid by Earth standards, but warm enough to flow as a viscous liquid until it eventually froze. Several specific features on Triton have been interpreted as cryovolcanic in origin. There are caldera-like depressions that resemble the collapsed centers of volcanic structures, with smooth interiors and steep walls. There are long, sinuous channels that could be the paths of past cryovolcanic flows, snaking across the surface in patterns that resemble lava channels on the Moon or terrestrial volcanic landscapes. There are domes that rise above the surrounding plains, with rounded profiles and dimensions of tens of kilometers across, possibly representing the solidified surface of erupted cryolava that has slowly cooled and frozen. None of these interpretations is certain. The image resolution, while spectacular by the standards of pre-Voyager knowledge, is still limited compared to what modern missions can achieve. Many features could be interpreted in multiple ways. But the cumulative weight of the evidence supports the idea that cryovolcanism has been a major force in shaping Triton's surface over the past several 100 million years. One of the most striking individual features identified in the Voyager 2 images is a structure that has been informally called the walnut because of its resemblance to the texture of a walnut shell. The feature is a roughly circular region, perhaps 200 kilometers across, with a complex pattern of ridges and grooves on its surface. It sits within a broader plain and appears to be elevated slightly above the surrounding terrain. The origin of the walnut is debated. Some researchers have suggested it represents a large cryovolcanic dome, possibly the surface expression of a single massive eruption. Others have proposed that it is a tectonic feature, the result of compression or extension in the ice shell. Still others have suggested that it might be the relic of a major impact whose original crater has been heavily modified by subsequent geological processes. Without higher resolution data, the question cannot be settled. The polar cap itself, beyond the streaks left by the plumes, shows evidence of complex history. The boundary between the bright cap and the darker surrounding terrain is irregular, with bays and peninsulas of nitrogen ice extending into the darker regions and isolated patches of dark material trapped within the bright zone. This boundary clearly shifts over time as the cap responds to seasonal variations in solar illumination. Triton's seasons are extreme because the Moon orbits Neptune in a plane tilted significantly relative to Neptune's orbit, and Neptune itself is tilted relative to its plane of motion around the Sun. The combined effect produces seasons on Triton that last decades, with each pole experiencing long periods of continuous sunlight, followed by long periods of continuous darkness. During the sunlit summer, nitrogen ice sublimates from the cap, thinning it and possibly removing some regions entirely. During the dark winter, nitrogen recondenses, rebuilding the cap. The exact balance is not well understood because no spacecraft has returned to observe how the cap has changed since 1989. Telescope observations from Earth, using modern instruments, have detected changes in the global atmospheric pressure of Triton, which is interpreted as evidence that the cap has been thinning over the decades since the Voyager flyby, releasing nitrogen gas into the atmosphere as the South Polar region experiences its long summer. The dynamism of the surface, combined with the active plumes and the possibility of a subsurface ocean, painted a portrait of Triton that was utterly unlike anything anyone had expected before the Voyager 2 encounter. The Moon was geologically alive in multiple ways. Its surface was being continuously modified by sublimation, condensation, plume deposition, and possibly cryovolcanic activity. Its interior was apparently warm enough to drive diapyrism and possibly to sustain a liquid layer. Its atmosphere, thin as it was an active part of a global cycle of mass and energy. The frozen, dead world of pre-Voyager expectations had been replaced by something far more complex and far more interesting. And the more the data was studied, the stranger Triton became. The next discovery would push the strangeness further still, into territory that scientists had not even known to anticipate. The fourth major discovery emerged from a careful examination of Triton's atmospheric and thermal data, and it presented a paradox that has defied complete resolution to this day. The paradox is that Triton's atmosphere, while undeniably real and undeniably structured, behaves in ways that should not be possible given the Moon's energy budget. The thin envelope of nitrogen gas surrounding Triton shows evidence of organized circulation, of layering, of temperature variations with altitude, of phenomena like clouds and hazes that on any other body would be considered straightforward, but here become difficult to explain. The atmosphere does too much with too little, and the question of how it manages this trick has been one of the persistent mysteries of the Voyager 2 encounter. The basic atmospheric measurements were obtained from several different instruments working in concert. The ultraviolet spectrometer detected emissions from atmospheric nitrogen and inferred the density profile of the upper atmosphere. The radio science team used the spacecraft's radio signal as it passed behind Triton from Earth's perspective, watching how the signal was bent and attenuated by the atmosphere, which provided a direct measurement of the pressure and temperature structure at lower altitudes. The imaging team identified clouds and hazes by their appearance against the surface and at the limb. The infrared spectrometer measured thermal emission from the surface and constrained the temperatures involved. Together, these measurements produced a coherent picture. Triton's atmosphere has a surface pressure of approximately 14 microbars, which is roughly 1,700,000 of Earth's atmospheric pressure at sea level. By any practical standard, this is a vacuum. A human standing on Triton's surface, ignoring the cold and the lack of breathable air, would experience essentially no atmospheric resistance to motion. Yet despite its tenuousness, the atmosphere has a measurable temperature structure. At the surface, the temperature is the famous -391 degrees Fahrenheit. Moving upward through the atmosphere, the temperature first decreases slightly, then increases significantly in the upper layers. By an altitude of several hundred kilometers, the temperature has risen to roughly -270 degrees Fahrenheit. This warming is associated with a region called the thermosphere, where solar ultraviolet radiation and energetic particles from Neptune's magnetosphere deposit energy into the thin gas. The presence of an organized thermal structure in such a thin atmosphere is itself notable. The atmosphere has so few molecules that conventional notions of temperature and pressure become somewhat strained. In Earth's atmosphere, temperature is well defined because gas molecules collide frequently and reach thermal equilibrium. In Triton's atmosphere, the collision rates are much lower, especially at higher altitudes, and the gas behaves in ways that are intermediate between a true fluid and a collisionless flow. That a thermal profile can be defined and measured at all is a tribute to the careful work of the Voyager 2 team and the analysts who followed. Within this thin atmosphere, the imaging team identified discrete clouds. They appeared as bright features against the darker surface in some images, with shapes that suggested condensation of some volatile compound. The clouds were generally located at low altitudes, within a few kilometers of the surface. Their composition was inferred from the atmospheric chemistry to be most likely nitrogen ice crystals, condensing from the gas as it cooled near the surface. The clouds are spatially limited, appearing only in certain regions and not as a global feature. They suggest that local variations in temperature and humidity, if such terms can even be applied to Triton's atmosphere, are significant enough to produce condensation in some places but not in others. Above the clouds, the imaging team detected a more pervasive haze. Unlike the discrete clouds, the haze was global, extending around the entire limb of the moon as a thin, slightly bluish layer. The composition of the haze is thought to be complex organic compounds, the tholins mentioned earlier, formed by the action of solar ultraviolet radiation on the methane and nitrogen in the atmosphere. The chemistry produces a variety of carbon-bearing molecules, some of which condense into aerosol particles that scatter sunlight and produce the observed haze. The hazes are stable enough to persist as a continuous feature of the atmosphere, suggesting that the production of organic compounds and the loss of haze particles to the surface are roughly in balance. The paradox arises when these atmospheric features are considered alongside the energy budget. Triton receives almost no solar radiation. The sunlight that does reach its surface is barely sufficient to maintain the polar cap, let alone drive significant atmospheric circulation. Yet the wind patterns inferred from the plume trails, from the surface streaks, and from the distribution of clouds suggest an atmosphere that is genuinely circulating, moving mass from one region to another in organized flows. Some of the circulation is driven by sublimation of nitrogen from the warmer parts of the polar cap and condensation in cooler regions, which produces a mass flow that resembles a kind of slow wind. But the details of the circulation, the formation of clouds at specific locations, the persistence of the global haze, all suggest a more complex system than a simple sublimation flow would produce. Even more puzzling is the evidence of seasonal change. Telescope observations from Earth, made in the decades after the Voyager 2 encounter, have detected variations in Triton's atmospheric pressure that cannot be readily explained by the simple seasonal models. The pressure appears to have roughly doubled between 1989 and the early 2010s, then begun to decline again. The most straightforward explanation is that the South Polar Cap, which was experiencing its long summer during the Voyager flyby, has been sublimating nitrogen ice into the atmosphere over the decades, raising the global pressure. As the seasons shift and the sun begins to move away from the South Pole, the sublimation slows and condensation in colder regions removes nitrogen from the atmosphere, lowering the pressure. The model is plausible, but the magnitudes involved, the rates of change, the spatial distribution of the cap are not all well constrained, and the observed changes have proven difficult to reproduce in detailed models. A second component of the paradox involves the upper atmosphere. The Voyager 2 measurements detected an ionosphere around Triton, a layer of charged particles produced by the ionization of atmospheric gases. The ionosphere on Triton is unexpectedly dense for such a thin atmosphere, with electron densities that rival those of much larger and more substantial atmospheres elsewhere in the solar system. The source of the ionization is the bombardment of the upper atmosphere by energetic electrons from Neptune's magnetosphere, which strike the nitrogen molecules and strip them of electrons. The magnetosphere is itself a strange environment, tilted at a large angle relative to Neptune's rotation axis and offset significantly from the planet's center, which means that Triton passes through different regions of the magnetosphere on different parts of its orbit. The varying environment produces variations in the ionosphere that are still not fully understood. The combination of clouds, haze, and organized thermal structure, evidence of seasonal change, and an unexpectedly dense ionosphere paints a picture of an atmosphere that is genuinely active. It is not a passive byproduct of surface sublimation. It is a system with internal dynamics, with feedback loops, with chemistry that operates at temperatures so low that most reactions on Earth would stop completely. The molecules in Triton's atmosphere find ways to interact, to combine, to condense, to be transporting, despite the extreme cold and the extreme thinness of their environment. The mystery deepens when one considers what drives the chemistry. The ultraviolet radiation from the sun, while weak, is sufficient to break down methane molecules in the upper atmosphere, producing carbon and hydrogen radicals that then combine into more complex compounds. These compounds eventually condense into the haze particles and fall to the surface, where they accumulate as a dark organic layer beneath the brighter ices. Over geological time, this accumulation could be substantial, producing the dark coloration seen on parts of the surface. The plumes then sweep some of this material back into the atmosphere, redistributing it across the polar cap as the dark streaks. The cycle suggests a complete system, a kind of slow chemical metabolism operating across the entire moon, with material moving from the upper atmosphere to the surface, across the surface by wind and plume deposition, and back into the atmosphere by sublimation and plume eruption. The system is not fully closed, of course, because solar radiation continuously drives the chemistry, and some material is likely lost to space over geological time. But it is more closed than anyone would have predicted before the Voyager 2 data was analyzed. The atmospheric paradox, like the question of the subsurface ocean, has resisted complete resolution because no spacecraft has returned to Triton to make follow-up measurements. The Voyager 2 data is a snapshot, frozen in time, of an atmosphere that has continued to evolve in ways that can only be inferred from distant telescope observations. The full picture, the dynamic system in all its detail, remains beyond our reach. The most shocking revelation from the Voyager 2 encounter, the one that reframed everything else, did not come from a single observation. It emerged from the synthesis of everything the spacecraft had measured, and it concerned not Triton itself, but Triton's relationship to Neptune and to the broader solar system. The revelation was that Triton's entire history, the violent capture, the global ocean, the geological activity, the strange atmosphere, all of it pointed to one inescapable conclusion. Triton was not just a moon, it was a survivor. A captured world that had retained, against all odds, the capacity to remain dynamically active billions of years after its original home had become irrelevant. And what that implied about the rest of the solar system was profound. The argument runs as follows. Before Voyager 2, planetary scientists generally divided the solar system into two broad categories. There were the inner worlds, the rocky planets and their moons, which were geologically active in various ways. And there were the outer worlds, the gas giants and the icy bodies beyond them, which were largely considered passive reservoirs of primordial material. The gas giants themselves had complex atmospheric dynamics, but their moons, with a few notable exceptions like Io and to some extent Europa, were thought of as essentially frozen. Their geological clocks had stopped early in solar system history. They were museums, not living worlds. The discovery of active volcanism on Io during the Voyager 1 encounter in 1979 had already begun to challenge this view. Io was clearly a living world, with eruptions visible in real time and a surface so young that no impact craters could be identified at all. But Io was special. It orbited close to Jupiter, the most massive planet in the solar system, and it was caught in a gravitational resonance with two other moons that maintained its eccentric orbit. The combination produced enormous tidal heating, enough to melt the moon's interior and drive the spectacular volcanic activity. Io's activity was understood as a special case, a product of unique circumstances that did not apply to other icy or rocky moons. Triton broke that framework. Triton is not in any obvious gravitational resonance with other moons. Its orbit, while retrograde, is almost circular today, providing very little tidal heating. By every conventional measure, Triton should not be geologically active. The energy required to drive plumes, to resurface vast regions of the moon, to sustain a subsurface ocean if one exists, should not be available. Yet the evidence from the Voyager 2 encounter is unambiguous. Something is providing that energy. Something is keeping Triton dynamically alive billions of years after its capture by Neptune. And the leading candidate is the same kind of process that operates inside the Earth, namely the slow decay of radioactive isotopes within the rocky core, combined with the insulating properties of the overlying ice. If this combination is sufficient to keep Triton active, then it is plausibly sufficient to keep many other large icy bodies active as well. The implications of this realization began to spread through planetary science in the years following the encounter. If Triton could harbor active geology and possibly a subsurface ocean despite being far from any major heat source, then perhaps Pluto, with its similar size and composition, might also be active. When the New Horizons spacecraft finally reached Pluto in 2015, 26 years after Voyager 2 passed Triton, it confirmed this prediction in spectacular fashion. Pluto turned out to have a young surface, mountains of water ice, vast plains of nitrogen ice that flow slowly like glaciers, and possibly a subsurface ocean of its own. Pluto and Triton, both of them survivors from the same general region of the early solar system, were revealed to be remarkably similar in their geological complexity. The pattern was confirmed. Beyond Pluto, the discovery extended to other Kuiper Belt objects. Bodies like Eris, Haumea, Makemake, and others that had previously been treated as essentially inert frozen worlds were now suspected of harboring their own internal activity. The implication is that there may be hundreds, possibly thousands, of dynamically active icy worlds in the outer solar system, each potentially with subsurface oceans, each potentially with conditions suitable for the chemistry that on Earth led to the origin of life. Triton, the only one any spacecraft had visited up close, was the first member of a vast and largely unexplored population. This is the shock that reframes everything. The solar system is not a system of a few active worlds surrounded by an empty reservoir of frozen relics. It may be a system in which active worlds are the norm, and the only reason we did not realize this before is that we had not visited any of the outer bodies up close. Triton revealed that the assumption of deadness was an artifact of our ignorance. Once we looked closely, the activity was obvious. The question that emerged was not why Triton was active, but rather how many other worlds like it were waiting to be discovered. The recognition of Triton's broader significance shifted the way planetary scientists thought about the search for life beyond Earth. The leading candidates for extraterrestrial habitats had traditionally been Mars, and more speculatively, the upper atmosphere of Venus. Both were considered because they were nearby and relatively easy to study. But the requirements for life as we know it are liquid water and a source of energy, and the inner solar system, apart from Earth, has very little liquid water available today. The outer solar system, by contrast, may have liquid water in abundance, locked away beneath the icy crusts of many moons and possibly many Kuiper Belt objects. If Triton has an ocean, and if similar oceans exist on Europa, Enceladus, Pluto, and countless other bodies, then the total volume of liquid water in the solar system is dominated by these subsurface reservoirs. Earth's oceans, by comparison, are a small fraction of the whole. This is a startling reframing. For most of human history, Earth was assumed to be unique in possessing surface oceans. The discovery that liquid water exists in vast quantities elsewhere, even if locked beneath ice, transforms the picture. It means that the conditions for life, at least the conditions of liquid water and energy, may be remarkably common. It does not mean that life is necessarily widespread. Many other factors are required, and the chemistry that produces life from non-living matter is still poorly understood. But the basic requirement of liquid water turns out to be far less restrictive than was once assumed. The solar system is, in a sense, a much wetter place than we used to think. Triton's role in this reframing is foundational. The Voyager 2 encounter was the first time a spacecraft examined a captured Kuiper Belt object up close. The discoveries made there were the first evidence that bodies in the outer solar system could be much more interesting than the conventional models had suggested. The subsequent missions to Europa, Enceladus, Pluto, and others have confirmed and extended the pattern, but Triton was the beginning. every discussion of habitability in the outer solar system, every proposed mission to look for life beneath the ice of a distant moon traces its conceptual lineage back to those few hours in August 1989, when Voyager 2 returned the first detailed images of Triton's astonishing surface. There is one more layer to this revelation that deserves attention. Triton, as a captured object, brings with it the chemistry and the history of the region where it formed, the outer solar system beyond Neptune's orbit. When Voyager 2 measured Triton's composition, the surface deposits of nitrogen, methane, water ice, carbon monoxide, and carbon dioxide, the spacecraft was effectively sampling a Kuiper Belt object. The compounds present on Triton's surface are characteristic of bodies that formed at very low temperatures in the cold outer reaches of the protoplanetary disk that gave rise to the solar system. They preserve information about the chemical conditions of that region billions of years ago, information that is otherwise difficult to obtain because the Kuiper Belt is so far away and so difficult to study in detail. Triton, in this sense, is a chemical time capsule, carrying ancient material to a location where it can be examined more easily, having been brought inward to Neptune's orbit by the violent dynamics of the early solar system. What Voyager 2 actually accomplished in a few hours of close approach was not merely the exploration of one strange moon. It was the first reconnaissance of an entire previously unknown category of worlds, a category that may dominate the solar system in terms of liquid water content and potential habitability. The shock of that realization, the recognition that the cold outer reaches of our cosmic neighborhood are far more dynamic and far more interesting than anyone had imagined, continues to reverberate through planetary science today. And the most extraordinary part is that this reframing was achieved by a spacecraft built in the early 1970s, with computers less powerful than a modern calculator, using a brief encounter that could not be repeated and has never been followed up. Triton is still, in 2026, the only Kuiper Belt-class object that humanity has ever seen up close in detail. Everything we have learned about that entire population of worlds rests on those few hours of data. What Triton changed was not one isolated model. It changed the entire way scientists thought about cold worlds. Before Voyager 2, distance from the sun was often treated almost like a sentence. The farther a world was from sunlight, the less active it was expected to be. Heat drove geology. Heat drove weather. Heat drove chemical change. Move far enough outward, and everything should slow down until it effectively stops. Triton shattered that assumption. The old model was simple. Small icy bodies were expected to lose their internal heat early. Their surfaces would freeze. Their atmospheres, if they had any, would collapse onto the ground as frost. Their craters would accumulate for billions of years, turning their surfaces into ancient records of impacts. That model made sense because it matched what scientists could see from a distance. Most outer solar system bodies looked dim, cold, and unchanged. But Voyager 2 revealed the flaw in that reasoning. They looked unchanged only because no one had ever seen them closely enough. Triton forced scientists to treat ice not as a passive material, but as geology. On Earth, rock bends, cracks, melts, rises, and erupts. On Triton, ice may play many of those same roles. Water ice can become bedrock. Nitrogen ice can become a seasonal cap. Methane ice can participate in atmospheric chemistry. Ammonia mixed with water can lower freezing points and create mobile materials deep below the crust. In the outer solar system, the materials are different, but the processes may be just as rich. This overturned the older idea that geological activity required Earth-like temperatures. Triton showed that activity can operate in slow motion under conditions that seem impossible to human intuition. A tiny amount of sunlight can drive sublimation if the material is volatile enough. A small amount of internal heat can matter if the ice shell is insulating enough. A thin atmosphere can move material if the particles are light enough. A surface can be renewed even when the temperature is hundreds of degrees below zero. The second theory Triton overturned was the idea that atmospheres must be thick to matter. Triton's atmosphere is almost nothing compared with Earth's, and yet it shapes the surface. It bends plumes. It carries dark particles. It supports hazes. It participates in seasonal pressure changes. It exchanges material with the polar cap. It is not a backdrop. It is an engine. A weak one by Earth standards, but a real one. That realization became important far beyond Triton. Pluto, decades later, would reveal a similar lesson. A world in the Kuiper Belt can have an atmosphere, glaciers, flowing nitrogen plains, mountains, haze layers, and seasonal changes. That did not make Pluto a copy of Triton, but it showed that Triton was not a freak accident. It was an early warning. The outer solar system was not dead. It was waiting for better cameras. Triton also changed the way scientists think about planetary categories. The word moon makes Triton sound secondary, almost like an accessory to Neptune. But Triton is larger than Pluto. It has its own atmosphere. It has a complex surface. It may have an ocean. It has a history more dramatic than many planets. Calling it simply a moon hides the truth. Triton is a captured world, a planet-like body forced into orbit around Neptune after a violent gravitational event. Its identity is not defined only by where it is now. It is defined by where it came from. And that matters because planetary science had often organized worlds by present location. A moon of Neptune belonged to the Neptune system. A Kuiper Belt object belonged beyond Neptune. A dwarf planet belonged in another category. Triton blurred those lines. It is a Kuiper Belt-type world inside Neptune's gravitational prison. It is both a moon and a stolen dwarf planet-class object. It is evidence that the early solar system was not orderly and calm, but chaotic, violent, and mobile. The capture of Triton also forced scientists to reconsider Neptune itself. If Triton was captured, then the original Neptunian moon system may have been destroyed. Ancient moons could have been thrown away, shattered, or driven into Neptune. Nereid's strange orbit may be a surviving scar from that event. Neptune's system today may not be the system it was born with. It may be the aftermath of a collision between histories. That is why Voyager 2's data still matters. It does not merely describe what Triton looked like in 1989. It describes a solar system where worlds migrate, collide, capture, freeze, thaw, and transform. It suggests that what we see today is not a static arrangement, but the surviving outcome of deep time. Every orbit is a clue. Every crater count is incomplete. Every surface is temporary. The most important change may be psychological. Before Triton, scientists had reasons to be cautious. They did not want to overstate what cold moons could do. They did not want to assume hidden oceans or active geology without evidence. But Triton showed that caution can become blindness. Sometimes the universe is not less active than we imagine. Sometimes it is more active, but in a form we did not know how to recognize. That is the legacy of Voyager 2's Triton encounter. It transformed icy moons from frozen leftovers into active worlds. It transformed volatile ices from surface coatings into geological materials. It transformed thin atmospheres from scientific footnotes into dynamic systems. And it transformed the Kuiper Belt from a distant population of icy objects into a reservoir of possible ocean worlds. The old question was, how can Triton possibly be active? The new question is much larger. If Triton is active, how many other frozen worlds are active too? The reason Triton matters to humanity is not because we will visit it soon. We will not. It is too far away, too difficult, too expensive, too demanding for any simple mission. Even light itself takes hours to cross the distance between Earth and Neptune. A spacecraft sent there would spend a large fraction of a human life just traveling. Triton is not close enough to become familiar. It remains remote, dark, and almost unreachable. And yet that distance is exactly why it matters. Triton reminds us that human intuition is local. We evolved on a warm planet, under a bright sun, surrounded by air, water, weather, soil, and familiar cycles. We think of activity in Earth terms. Rivers flow because water is liquid. Volcanoes erupt because rock melts. Clouds form because air is thick enough to carry moisture. Seasons unfold over months. Landscapes change in ways we can see. Triton operates under an entirely different set of rules. Its rivers, if it ever had them, would not be made of water at the surface. Its active materials are ices. Its atmosphere is thinner than most laboratory vacuums. Its seasons last for decades. Its surface changes at temperatures where ordinary Earth chemistry would seem asleep. That forces a humbling realization. The universe does not need to resemble Earth in order to be complex. It does not need warmth in order to change. It does not need comfort in order to become interesting. Complexity is not a privilege of habitable surfaces. It can emerge in darkness, in deep cold, under faint sunlight, beneath ice, inside worlds that look dead from afar. This matters for the search for life because life is not only a question of where sunlight reaches. For centuries, sunlight seemed essential. On Earth, nearly every food chain ultimately depended on photosynthesis. Plants captured sunlight. Animals consumed plants or other animals. Life was tied to the surface, to warmth, to light. Then scientists discovered ecosystems around hydrothermal vents on the ocean floor where sunlight never reaches. Their chemical energy from the interior of the Earth supports entire communities. That discovery changed biology. Worlds like Triton extend that lesson into space. If a subsurface ocean exists beneath Triton's ice, then it would be completely cut off from sunlight. It would not have blue skies or waves under starlight. It would exist in darkness, under crushing pressure, sealed beneath miles of frozen material. But it might have liquid water. It might have dissolved salts. It might have chemical gradients. It might have heat leaking from a rocky core. Those ingredients do not prove life, but they make the question serious. And once the question becomes serious on Triton, it becomes serious across the outer solar system. This is why the discovery is emotionally powerful. It expands the possible places where nature can experiment. Earth is no longer the only obvious stage for complex chemistry. Mars is no longer the only nearby world worth asking about. The deep solar system, once imagined as a frozen storage room, becomes a hidden archipelago of possible oceans. Europa, Enceladus, Ganymede, Callisto, Titan, Pluto, Triton, perhaps many others too small or too distant to study properly. The map of habitability changes, but Triton also matters because it shows how much can be learned from a brief encounter. Voyager 2 did not orbit Triton. It did not land. It did not drill. It did not sample plumes directly. It passed by once, at high speed, with agging instruments, under dim sunlight, and then it was gone forever. The entire modern scientific understanding of Triton rests on that fleeting passage. A few hours of data have sustained decades of research. There is something almost uncomfortable about that. Humanity's knowledge of one of the most important ocean world candidates in the solar system depends on a single flyby from 1989. The images are precious because there are no replacements. The gaps are enormous because the encounter could only see part of the surface. The northern hemisphere was poorly observed. Seasonal changes could not be followed. Plumes could not be monitored. The atmosphere could not be watched over decades from close range. Every model is built around absence as much as evidence. That is why Triton carries a strange emotional weight. It is not only mysterious because it is complex. It is mysterious because we looked once and then left. We saw enough to know it mattered, but not enough to understand it. It is like hearing one sentence from a book written in an unknown language, realizing the book may contain something profound, and then losing access to the library. For humanity, Triton is a lesson in patience. Space exploration does not move at the speed of curiosity. A question can be asked in 1 decade and remain unanswered for half a century. A spacecraft can reveal a mystery before the technology, funding, and political will exist to solve it. Generations of scientists can inherit data from a mission launched before they were born. The timeline of discovery becomes larger than individual lives. And still, that is not a reason for despair. It is part of what makes exploration meaningful. Voyager 2 was built by people who knew they might not live to see every consequence of its work. The spacecraft was launched into uncertainty. It returned discoveries that outlasted careers. It changed textbooks. It redirected mission proposals. It shaped the imagination of scientists who were children when the flyby happened. Triton matters because it reminds us that one act of exploration can echo for decades. A machine can pass a world once and permanently alter the way a species understands its cosmic neighborhood. A few images can turn a frozen moon into a scientific frontier. A plume seen against the blackness of space can change what we think is possible. And perhaps the deepest reason Triton matters is this. It makes the universe feel less empty, not less vast, not less cold, not less dangerous, but less empty. The outer darkness is not just darkness. It contains weather, chemistry, motion, hidden oceans, ancient captures, surfaces that renew themselves, atmospheres that breathe in slow, seasonal pulses, worlds that remember the violence of their formation and still carry energy from it billions of years later. Triton tells us that even at the edge of sunlight, the solar system is not finished becoming itself. And yet, for all that Voyager 2 revealed, the most important facts about Triton remain unknown. That is the frustrating truth at the center of the story. Scientists do not lack theories. They have too many theories. What they lack is the one thing no model can replace: new measurements. The first unanswered question is the simplest. Are the geysers still erupting? Voyager 2 saw active plumes in 1989, but that was one season, one hemisphere, one moment in Triton's long orbital cycle around the Sun. The South Polar region was experiencing summer. Sunlight, faint as it was, fell continuously on the nitrogen cap. If the solid-state greenhouse model is correct, then the plumes may be seasonal. They may shut down as the South Pole moves away from sunlight. They may migrate toward other regions. They may reappear near the opposite pole many decades later, or they may not. No one knows. The second question is what truly powers those eruptions. Solar heating explains much, but not everything. Internal heat explains much, but may not be necessary. A future mission would need to observe vents at high resolution, measure plume composition directly, monitor changes over time, and determine whether eruptions are linked to sunlight, terrain type, subsurface structure, or something else entirely. Without those measurements, the geysers remain trapped between two possible explanations. The third question is whether Triton has an ocean today. This is the question that would transform Triton from a strange icy moon into one of the most important astrobiological targets in the solar system. A future spacecraft could search for an induced magnetic field, the kind of signature produced when a salty subsurface ocean conducts electricity as it moves through Neptune's magnetic environment. It could measure Triton's gravity field to determine how mass is distributed inside the moon. It could map surface deformation. It could look for regions where the crust appears thin, mobile, or recently resurfaced. It could test whether the ocean is a serious present-day possibility or only a remnant of ancient heat. The fourth question is the nature of the cantaloupe terrain. No one has seen it at modern resolution. The Voyager images are extraordinary, but they are not enough. Are the dimples formed by diapias rising through the ice shell? Are they collapse features? Are they related to convection, cryovolcanism, tectonic stress, or ancient resurfacing? Do they exist across the unseen hemisphere, or only in the regions Voyager photographed? Are they young, old, or continuously renewed? Triton's most famous landscape is still almost entirely unexplained. Then there is the Northern Hemisphere, one of the greatest missing chapters in planetary exploration. During the Voyager 2 flyby, much of Triton's north was in darkness or poorly illuminated. That means an entire half of the moon remains largely unknown at close resolution. It could contain older cratered terrain. It could contain different polar deposits. It could contain more cantaloupe terrain, more cryovolcanic features, more plume vents, or something completely unfamiliar. The map of Triton is not complete. It is a partial portrait mistaken, too often, for a finished world. The atmosphere raises its own set of unanswered questions. How does the pressure change over Triton's seasons? How much nitrogen moves from one pole to the other? How thick are the haze layers? What is their particle size? What organic compounds are being produced? How much material escapes into space? How does Neptune's magnetosphere alter the upper atmosphere? How does that changing ionospheric environment affect surface chemistry over millions of years? These are not minor details. They are the mechanisms by which Triton evolves. This is why mission concepts keep returning to Triton. NASA's Strategic Guidance Materials list Neptune Odyssey and Triton Ocean World Surveyor among formal mission concept studies, and the Triton Ocean World Surveyor concept specifically describes a Neptune orbiter architecture that would conduct dozens of close science flybys of Triton rather than one brief pass. The difference between a flyby and an orbiter would be enormous. Voyager 2 saw Triton once. An orbiter could watch it over time. It could return to the same regions under different lighting. It could compare plume activity from one flyby to another. It could map the whole surface. It could measure the atmosphere repeatedly. It could study how Triton interacts with Neptune's magnetosphere at different orbital positions. It could turn a snapshot into a movie, but getting there is difficult. Neptune is far. A mission to the Neptune system requires years of crews, gravity assists, radioisotope power, advanced telecommunications, radiation-hardened electronics, and long-term operational planning. The spacecraft would have to survive in deep space for well over a decade before the main science even began. If it entered orbit around Neptune, it would need a massive maneuver or a clever mission design to slow down enough to be captured. Every option is expensive. Every trajectory is constrained by planetary alignments. Every delay can shift arrival by years. That is why Triton remains in a strange position. Scientifically, it is one of the most compelling worlds in the solar system. Practically, it is one of the hardest to reach. The result is a painful gap between importance and accessibility. Scientists can make the case. Engineers can design the missions. Reports can be written. Instruments can be proposed. But until a mission is selected, built, launched, and flown for more than a decade, Triton remains what it has been since 1989, a mystery preserved in old data. And the clock is not standing still. Triton's seasons continue. Its atmosphere changes. Its polar caps shift. The plumes, if they are seasonal, may already have altered or stopped. The surface that Voyager saw may not be the surface a future spacecraft sees. That is scientifically exciting, but also troubling. We do not have a baseline. We do not know what has changed because we were not there to watch. This may be the most unsettling, unanswered question of all. What has Triton done since Voyager left? For almost 4 decades, while humanity built the internet, launched space telescopes, landed rovers on Mars, orbited Saturn, flew past Pluto, and returned samples from asteroids, Triton has continued in silence around Neptune. Its atmosphere has expanded and contracted. Frost has migrated. Organic haze has fallen. Dark deposits have shifted. Its interior, if an ocean exists, has continued pressing upward against the ice. Its plumes may have erupted under skies no spacecraft could see. The next mission to Triton will not simply continue Voyager's work. It will arrive at a different world. There is a philosophical unease in Triton's story that goes beyond the science. It comes from the fact that Triton is both known and unknown, both mapped and unmapped, both familiar and unreachable. We have images of its surface. We have measurements of its atmosphere. We have names for its terrains. We can calculate its orbit with precision. And yet, in the most important ways, it remains a stranger. Triton is a world with a stolen history. It did not begin where it now resides. It formed somewhere in the outer darkness, among the icy bodies beyond Neptune, then was captured by a planet powerful enough to rewrite its fate. That capture was not gentle. It likely reshaped the entire Neptunian system. It heated Triton from within. It may have melted it. It may have destroyed other moons. It turned a wandering outer solar system body into Neptune's dominant satellite. Every time Triton circles Neptune, it carries the memory of that ancient violence. There is something deeply strange about that. The solar system often looks orderly from a distance. Planets orbit in clean ellipses, moons circle planets, the architecture seems stable. But Triton reminds us that the present order is only the surface of a much wilder past. Worlds have migrated, orbits have shifted, bodies have been captured, scattered, shattered, and lost. What looks calm now may be the aftermath of chaos. In that sense, Triton is not only a moon, it is evidence. Evidence that the early solar system was not built like a machine, but shaped like a storm. Neptune did not merely acquire Triton. It was changed by Triton. And Triton, in turn, was transformed by Neptune. Two histories collided, and the result is still visible billions of years later in plumes, ice, atmosphere, and orbit. The deeper philosophical lesson is that worlds are not defined only by their present conditions. A place can be cold now because it was once violently heated. A surface can look young because ancient energy still echoes through it. A moon can seem quiet because the processes shaping it operate over time spans longer than civilization. Triton's present cannot be understood without its past, and that is true of planets, of moons, of stars, and perhaps of us. Voyager 2's encounter also reveals something about the limits of human knowledge. We often imagine ignorance as darkness before discovery and knowledge as light afterward. But Triton shows that discovery can create a deeper form of mystery. Before Voyager, scientists did not know what Triton looked like. After Voyager, they knew enough to understand that they did not understand it. The mystery did not shrink. It became sharper. That is the paradox of exploration. The first close look rarely provides final answers. It usually reveals better questions. A distant point of light becomes a landscape. A landscape becomes a geological problem. A geological problem becomes an interior model. An interior model becomes a question about oceans and habitability. Every answer opens a new chamber of uncertainty. This is not a failure of science. It is science working exactly as it should. A model is not a monument. It is a tool. Voyager 2 broke old models because the universe gave better evidence. The correct response was not to defend the old assumptions, but to build new ones, more flexible, more complex, more honest about uncertainty. Triton is still not properly explained because the data is incomplete, but the incompleteness itself is productive. It tells us where to look next. There is also something moving about the scale of the achievement. A spacecraft built before laptops, before smartphones, before modern digital cameras, before most of today's planetary scientists were born, passed a distant moon for a few hours and saw enough to alter human understanding. It did not understand what it saw. It did not interpret the images. It did not know it had found geysers, cantaloupe terrain, a possible ocean world, and a captured remnant of the Kuiper Belt. It simply measured, recorded, transmitted. The meaning came later, on Earth, in rooms full of scientists staring at grainy images arriving line by line. Meaning came through argument, calculation, doubt, correction, and decades of reanalysis. Voyager 2 was not only a machine moving through space. It was an extension of human curiosity, carrying our senses into a place our bodies could never survive. And perhaps that is why Triton feels so haunting. It exists at the edge of the reachable. We have been there, but only barely. We touched it with instruments, not hands. We saw it in passing, not in residence. We know enough to feel connected to it, but not enough to feel satisfied. It remains suspended in the imagination as one of those places where the universe seems to be withholding its final explanation. From Triton, the sun is not a blazing disk. It is a brilliant star, far away, giving less than 1,000th of the light Earth receives. Daylight, there would feel like deep twilight. The sky would not be blue in any familiar sense. The atmosphere would be too thin, the cold too extreme, the horizon too alien. Neptune would dominate the sky, vast and blue, a planet many times wider than our moon appears from Earth. Beneath that sky, nitrogen frost would glitter across plains sculpted by processes we still cannot fully describe. And somewhere, perhaps, beneath miles of ice, there may be an ocean that has never seen the sun. That image changes the emotional meaning of the outer solar system. It is not just the realm of distance. It is the realm of hiddenness. The most important things may not be visible from orbit. They may lie under crusts, beneath caps, inside worlds whose surfaces look frozen but whose interiors remain unresolved. The solar system may be filled with sealed oceans, buried chemistries, and slow geological pulses that no human eye has ever witnessed. Triton teaches that the universe does not owe us simplicity. It does not arrange itself according to what seems reasonable from Earth. It is stranger, older, more patient, and more inventive than our expectations. And sometimes, the only way to learn that is to send a small machine into the dark and let it look back. So what did Voyager 2 detect around Triton that NASA still cannot properly explain today? It detected a world that should have been frozen into silence, but was not. It detected plumes rising from nitrogen ice in a place where almost no heat should exist. It detected dark streaks laid down by winds in an atmosphere thinner than almost any human idea of weather. It detected a surface too young for its age, too complex for its temperature, too active for its distance from the sun. It detected cantaloupe terrain, a landscape so strange that even now there is no universally accepted explanation for how it formed. It detected a polar cap made of volatile ices, bright and pink and seasonally alive. It detected atmospheric haze, clouds, ionospheric structure, and chemical cycling in a place that should barely have an atmosphere at all. It detected evidence that the moon's history was not simple formation, but violent capture, tidal heating, possible internal melting, and long-term evolution. And most importantly, it detected the outline of a larger truth. Triton is not an exception that can be easily dismissed. It may be part of a hidden class of worlds, icy, distant, chemically rich, internally active, and possibly ocean-bearing. Worlds that do not fit the old imagination of the solar system. Worlds that force us to think differently about heat, habitability, geology, and time. That is why Triton still matters in 2026. Not because everything about it is known, but because so much remains unknown. Science often advances through clean answers, but sometimes it advances through stubborn mysteries that refuse to disappear. Triton is one of those mysteries. Every attempt to explain it reveals another layer. Every model answers one question and raises three more. Every comparison with Pluto, Enceladus, Europa, or other icy bodies makes Triton seem less isolated and more important. There is no final explanation yet for the plumes, no final explanation for the cantaloupe terrain. No confirmation of the ocean, no complete map of the surface, no long-term record of its seasons from close range, no direct sampling of its atmosphere or haze, no modern images of the vents, no spacecraft waiting near Neptune watching Triton change. All we have is Voyager 2, a spacecraft from another technological age, a machine with primitive computers, agging cameras, fadding power, and a transmitter weaker than a household light bulb. It flew past Triton once, gathered what it could, and vanished into the outbound darkness below the plane of the solar system. It will never return. It will never see another planet. It will continue traveling through interstellar space long after its final signal has faded. But for a few hours in August 1989, it looked at Triton. And that was enough. Enough to turn a point of light into a world. Enough to turn a dead moon into an active frontier. Enough to make scientists reconsider the outer solar system. Enough to suggest that the coldest places may not be the simplest places. Enough to leave behind a mystery that has lasted for decades. There is something almost poetic in the fact that Triton's greatest secrets were glimpsed only briefly. A world spent billions of years circling Neptune in the dark. Humanity sent one spacecraft. It passed once. The moon revealed just enough to change everything, then slipped back into distance. Since then, Triton has continued its silent orbit. Neptune rises and sets in its sky. Nitrogen frost migrates across its surface. Its atmosphere thickens and thins with the seasons. Organic haze settles slowly onto the ice. Somewhere, perhaps, vents still rupture beneath the polar cap. Somewhere, perhaps, a subsurface ocean presses quietly against the frozen shell above it. Somewhere, perhaps, chemistry is unfolding in darkness, unseen by any instrument. And here on Earth, we wait with the old data. We enhance the images. We rerun the models. We compare Triton to Pluto, to Enceladus, to Europa, to every new icy world that reveals itself as more complex than expected. We ask whether the plumes were seasonal, whether the ocean is real, whether the cantaloupe terrain formed from rising ice, collapsing crust, or a process no one has yet imagined. We ask what the northern hemisphere looks like. We ask what Voyager missed. That may be the most powerful part of the story. Voyager 2 did not close the book on Triton. It opened it. The next mission, whenever it comes, will arrive not at a blank target, but at a world already charged with questions. It will not ask whether Triton is interesting. Voyager answered that. It will ask why Triton is interesting. It will ask how long it has been active. It will ask what is hidden beneath the ice. It will ask whether the distant outer solar system is filled with other worlds like this one. Until then, Triton remains suspended between discovery and explanation. A moon that should be dead, but is not. A captured world that still carries the energy of its past. A frozen surface marked by motion. A thin atmosphere that behaves like a system. A possible ocean world orbiting a blue planet almost 3 billion miles from the sun. And maybe that is why the Voyager 2 encounter still feels unfinished. Because the greatest discoveries do not always give us closure. Sometimes they give us a doorway. Triton is one of those doorways. It opens onto the unknown outer solar system, onto hidden oceans, onto the chemistry of cold worlds, onto the possibility that activity and complexity are far more common than we once believed. If this story left you with the same sense of wonder that scientists felt when those first images arrived from Neptune, take a moment to like this video, subscribe to the channel, and share your thoughts in the comments. What do you think is really happening beneath Triton's surface? Are the geysers powered by sunlight, by internal heat, or by something we still have not understood? And should Triton be one of NASA's next great destinations? Because somewhere, far beyond the orbit of Uranus circling Neptune in the dim blue light of the outer solar system, Triton is still there. Cold, bright, restless, and unexplained.